Welcome to this tutorial about attenuation, amplification, and how to calculate the optical power budget for an optical link. When a light wave is traveling along a fiber, it loses some of its energy. The signal is attenuated as a result of absorption and scattering. Some energy is always lost in the joint between transceiver and fiber. We call this connector loss. Energy is lost in the fiber itself. This is called fiber loss. And at each point where the fiber is sliced, we get splice loss. The fiber loss in turn depends on the fiber type and its length, but also on additional factors such as the age of the fiber and if it is bent in curves when deployed. To calculate the distance an optical signal and a WDM system can cover, we need to know the strength, the power of the incoming signal, how much it is attenuated, and the sensitivity of the receiver. We normally measure power in watts, but for optical systems, a better unit of measure is the decibel. A decibel, abbreviated dB, is a relative unit of measurement. It expresses the ratio of two values of power on a logarithmic scale. Two signals whose level differ by 1 decibel have a power ratio of 10 to the power of 1/10, which is approximately 1.26. That is, an increase in power of 1 decibel makes the signal 1.26 times more powerful. Sometimes we want to express an absolute power level in decibels. We then use the unit decibel milliwatts, abbreviated dBm, with the power level still expressed in decibels, but now with reference to 1 milliwatt of power. That is, 1 dBm is 1.26 times 1 milliwatt, that is 1.26 milliwatts. The output power of a transceiver and the sensitivity of a receiver are normally expressed in dB, since we are talking about absolute power levels there. Let us look at the power budget for a simple optical link. The link has a transmitter, that is a transceiver, at one end, and a receiver, that is another transceiver, at the other end. The transmitter is connected to a short patch cord which leads to a multiplexer, which then connects to the fiber cable. The fiber cable in its turn is spliced in the middle, and then via a demultiplexer and patch cable connected to the receiver. At each connector along the link, we get a connector loss. Then the fiber introduces a loss that increases with distance, and some signal is lost in the multiplexer and demultiplexer. By adding up these losses, we can calculate the total link loss in decibel. The transmitter launches light with a given power, measured in dBm, into the first patch cord. At the other end of the link, the receiver has a minimum sensitivity, also measured in dBm. The difference between the transmitter output power and the receiver sensitivity makes up the optical power budget. That is, the amount of power measured in decibels that can be spent on losses along the link. If that loss is less than the available power budget, the receiver will be able to detect the signal. If the loss is greater than the budget, the signal is too weak to be detected by the receiver. The connector, patch cable, and splice losses typically add up to about 1 decibel. The mux and demux losses vary, but a starting point is to allocate 2 to 4 decibels to each of them. Typical fiber loss is 0.25 decibel per kilometer. A more precise fiber loss value can often be obtained from the fiber provider if the fiber is being leased, or it can be measured by a special instrument called an optical time domain reflectometer. Current technologies allow optical signals with gigabit per second data rates to travel up to about a kilometer over multi-mode fiber. Hence, such fibers are less suitable for use in telecommunication systems. On a single-mode fiber, an unamplified 10 gigabit per second signal from a transceiver can easily travel more than 100 kilometers and still be correctly detected. This is, however, not always enough. Hence, optical amplification or electrical regeneration of the signal may be needed along the way. An optical amplifier is coupled directly to the fiber and amplifies the amplitude of the light pulses that passes it. Optical amplification can extend the optical reach over single-mode fiber up to 800 kilometers or even more if the link is using forward error correction, FEC. Unfortunately, optical amplification adds noise to the signal at every amplifier, which reduces the signal-to-noise ratio. Consequently, after adding several optical amplifications, the signal is hidden in noise. This can be remediated by converting the optical signal back to an electrical signal, and then using electronics to amplify and reshape the signal before it is retransmitted again as an optical signal. This job is done by an optical regenerator, or OEO regenerator for short. An optical amplifier amplifies all DWDM wavelengths and is therefore a less costly alternative than an OEO regenerator, which must have discrete circuitry for each regenerated wavelength. The optical amplifier is also independent of any type of bitrate and framing of the transmitted signal. That is, it is fully bitrate and protocol transparent. The optical amplifier uses any of several possible physical mechanisms to directly amplify the light signal. The erbium-doped fiber amplifier, EDFA, is the most common type of optical amplifier in communication systems, as its amplification range coincides with the transmission window around 1,550 nanometers of silica-based optical fiber used by DWDM. An EDFA amplifier uses energy from an external source, the pump laser, to excite ions in the active medium, in this case, a piece of erbium-doped fiber, and the optical signal is amplified through interaction with the excited ions in the fiber. An EDFA is only applicable for wavelengths around 1,550 nanometers. Hence, only DWDM can be used in optically amplified networks. CWDM networks are optically unamplified networks. The power balance, that is, ensuring that the signal levels of all transmitted wavelengths are equal and does not interfere, is of utmost importance in amplified DWDM systems. Unfortunately, the EDFA amplifier is an unlinear device, which does not treat all wavelengths equal. The EDFA is therefore normally complemented by some type of optical channel equalizer that evens out the power differences between wavelengths. Another component in optically amplified networks is the variable optical attenuator, VOA, that balances the output power from the amplifier. The VOA is normally used together with an optical channel monitor, OCM, which measures optical power levels of the wavelengths used by DWDM and creates an automatic feedback loop, controlling the overall power level of the optical signal sent over the fiber. Optical amplifiers can be placed at various positions along the optical link, depending on where electrical power and space is available. An inline amplifier is placed between sites, a booster amplifier is placed at the sending site of the link, and a preamplifier is placed at the receiving end. Irrespectively of the position, all optical amplifiers serve to extend the reach of the optical signal and to balance the power between the DWDM wavelengths. The amplifiers are completely transparent to any type of bitrate and protocol, and can be configured to automatically balance the power levels for optimal signal transmission. This ends this tutorial. To learn more about optical communications, just continue with the next tutorial in this series.